Welcome to Cosmos and Dreams. Tonight, we explore a hidden rule of the universe, how formless clouds of gas, across billions of years, quietly collapse, ignite, and weave themselves into the spiraling cosmic cities we call galaxies, in ways science still cannot fully explain. If the universe is your kind of bedtime story, subscribe before you drift off. Now get comfortable, close your eyes, and let science carry you to sleep. Opening meditation. Close your eyes now, if you haven't already. Let your body settle into whatever surface is holding you. Feel the weight of your limbs release, just a little. Feel the quiet of the room around you, the soft darkness, the stillness of the air. Tonight, we are going to travel somewhere vast. Somewhere so immeasurably large that the human mind cannot fully grasp it, and yet, somehow, the human mind built the tools to understand it. We are going to follow the story of galaxies. Those enormous islands of stars, hundreds of billions of them, scattered across the observable universe like embers from some ancient, unimaginable fire. Each galaxy is a world unto itself. Each one holds within it the history of everything that ever existed inside it, every star born and extinguished, every planet formed from cooling dust, every possible chance that life might have found its footing somewhere in the dark. And the story of how they came to be, how they grew, how they changed over 13 billion years, that story is one of the most beautiful things science has ever tried to understand. You don't need to hold on to every detail tonight. You don't need to remember every name or every number. Simply let the words wash over you like the light from a distant star, ancient, quiet, and somehow still arriving. Let everything else drift away now. The universe is waiting. Part 1, Before the Galaxies, the Darkness at the Beginning. To understand how galaxies form, we must first travel back to a time before they existed at all. Back to a universe that contained nothing we would recognize. No stars. No planets. No light to speak of. Only a vast, hot, expanding sea of matter and energy, a universe in its infancy, still finding its shape. This was the state of the cosmos roughly 13.8 billion years ago. The Big Bang had occurred, though calling it a bang misrepresents it rather significantly. It was not an explosion in space. It was an expansion of space itself. The very fabric of the universe, inflating outward from a state of unimaginable density and temperature, carrying everything within it along for the ride. In those first fractions of a second, the universe was a churning plasma of quarks and leptons, the fundamental building blocks of matter, too energetic to bind together into anything so orderly as atoms. The temperature was incomprehensibly high. Billions upon billions of degrees. And the universe was expanding so rapidly that what had been incomprehensibly small became incomprehensibly large in less time than a heartbeat. Within the first few minutes, as things cooled slightly, protons and neutrons began to bind together. Hydrogen nuclei. Helium nuclei. A trace of lithium. This is the story of Big Bang nucleosynthesis, the forge at the beginning of time, where the lightest elements were built before the universe had even settled into its first chapter. But these nuclei were still surrounded by a dense fog of electrons. The universe was opaque, filled with so much charged particle matter that light could not travel freely through it. A photon of light would be absorbed and re-emitted almost immediately, bouncing endlessly through the plasma, going nowhere in particular. This continued for roughly 380,000 years. Nearly 400,000 years of cosmic fog, of a universe that was bright internally but utterly opaque to any hypothetical observer. And then something remarkable happened. Something cosmologists call recombination. As the universe expanded and cooled, the temperature finally dropped to a point, around 3,000 degrees, where electrons could no longer resist the pull of atomic nuclei. They were captured. Atoms formed for the first time. Hydrogen atoms. Helium atoms. And in that moment, the fog cleared. Light, photons that had been trapped, bouncing endlessly through that plasma, was suddenly free to travel in straight lines across the universe. The cosmos became transparent. And all that light, released at that single moment of recombination, is still traveling today. We can detect it. We call it the cosmic microwave background radiation. It is the oldest light in the universe, a faint, almost perfectly uniform glow of microwave radiation coming from every direction in the sky, a photograph of the universe when it was a newborn. But here is the crucial detail for our story. The cosmic microwave background is not perfectly uniform. When we look at it with extremely sensitive instruments like the COBE satellite, launched in 1989, or the Planck satellite, operational from 2009 to 2013, we see tiny variations. Temperature fluctuations of 1 part in 100,000. Barely perceptible ripples in the otherwise smooth fabric of the early universe. These ripples are everything. These tiny, almost invisible fluctuations in density in the early universe are the seeds of all structure. They are the reason galaxies exist at all. Where the early universe was ever so slightly denser, gravity would eventually pull more matter in. Over millions of years, these regions would grow. They would attract more and more material. And slowly, over hundreds of millions of years, these overdense regions would collapse inward, becoming the first stars, the first galaxies, the first great structures of the cosmos. But before the first stars could ignite, the universe passed through an era cosmologists call the cosmic dark ages. Imagine vast clouds of gas hundreds of light years across, moving almost imperceptibly slowly by human standards, but inexorably, drawn together by the one force that never switches off, the one force that acts across any distance. Gravity. For perhaps 200 million years after recombination, the universe remained in this quiet, lightless state. No stars burned. No galaxies glittered. Only those gentle drifting clouds of gas, moving slowly through the dark, beginning to gather, beginning to concentrate, beginning to build the structures that would eventually wake the universe from its long, dark sleep. The physicist Avi Loeb, of Harvard University, has written beautifully about this era. He calls it the universe's own kind of sleep, a deep cosmic rest before the first light would pierce the darkness and change everything. What ended the dark ages was the ignition of the first stars. And that moment, the moment when the first thermonuclear fire lit up the universe after 200 million years of darkness, is one of the most profound events in the history of the cosmos. We believe the first stars were massive. Far more massive than the stars we see today. Perhaps hundreds of times the mass of our own sunday. They burned ferociously hot and fast, living for only a few million years before exploding as supernovae or collapsing into black holes. They were made almost entirely of hydrogen and helium, the only elements that existed at that time. And because they contained no heavy elements to cool the gas as it collapsed, the clouds that formed them could not fragment into smaller pieces. They became giants. These first stars, astronomers call them population 3 stars, have never been directly observed. They lived and died too long ago, too far away, too briefly to have left easily detectable traces. But their indirect signature is everywhere. The heavy elements they forged in their cores and scattered in their deaths, carbon, oxygen, silicon, iron, those are the raw materials of everything that came afterward. Of every star that formed after them. Of every planet. Of every living thing. The story of galaxies begins here, in this dark age before the first light. It begins with those tiny ripples in the cosmic microwave background. With those clouds of gas slowly gathering in the dark. With the first stars igniting like matches struck in an ancient room. Part 2, The Architecture of the Cosmos, Dark Matter and the Cosmic Web. When the first astronomers began mapping the universe in earnest, in the 20th century, they noticed something deeply puzzling. Galaxies were not scattered randomly through space. They were gathered into clusters. And clusters were gathered into superclusters. And superclusters were arranged in vast sheets and filaments, thin walls of galaxies stretching across hundreds of millions of light-years, surrounding enormous voids where almost nothing existed at all. This structure, the cosmic web, as it came to be called, was not something anyone had predicted. It emerged from the data like a revelation. Surveys of the sky, particularly the CFA Redshift survey conducted by Margaret Geller and John Huckra at the Harvard-Smithsonian Center for Astrophysics in the 1980s, revealed what appeared to be a bubble-like structure to the universe. Galaxies arranged on the surfaces of great bubbles, like the skin of soap foam, with enormous empty voids stretching between them. It was one of the most striking images in the history of astronomy. The universe, mapped in 3 dimensions for the first time, looked like something alive, like the cross-section of a vast, intricate biological structure. A web of filaments and nodes, with emptiness between. But what was responsible for this structure? What had shaped the distribution of matter across billions of light-years into such a precise, organized pattern? The answer, we now believe, lies in something we cannot see. Something that does not emit light, does not absorb light, does not interact with ordinary matter in any way that we can directly detect, except through gravity. We call it dark matter. The story of dark matter's discovery is one of the great detective stories of modern science. It begins, in a sense, with a Swiss astronomer named Fritz Zwicky, working at Caltech in the 1930s. Zwicky was studying the Coma cluster, a vast congregation of galaxies, and he was measuring how fast those galaxies were moving. What he found disturbed him. The galaxies were moving far too fast. If the only mass in the cluster were the visible stars and gas, those galaxies should have flown apart long ago. Something invisible must be providing additional gravitational glue, holding the cluster together. Zwicky called it Dunkel Materie, dark matter. But few people paid much attention. His observation was noted and largely set aside. It wasn't until the 1970s that the evidence became truly compelling. An astronomer named Vera Rubin, working with her colleague Kent Ford at the Carnegie Institution in Washington, was studying the rotation of spiral galaxies. She was measuring how fast stars at different distances from a galaxy's center were moving, the galaxy's rotation curve. According to normal physics, the same physics that governs the orbits of planets in our solar system, stars far from a galaxy's center, where there is less mass inside their orbits, should move more slowly. Just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. But that was not what Rubin and Ford found. The rotation curves of spiral galaxies were flat. Stars far from the center were moving just as fast as stars near the center. The rotation speed did not fall off with distance, which meant that the amount of mass enclosed by each orbit was continuing to increase even as you moved far out into the galaxy, into regions where there were very few visible stars. Something invisible was out there. A vast halo of unseen matter surrounding each galaxy, extending far beyond its visible edge, providing the gravitational force needed to explain the motions of the visible stars. Dara Rubin spent decades refining these observations, measuring galaxy after galaxy, finding the same result every time. The evidence for dark matter became overwhelming. And though dark matter has never been directly detected as a particle, despite decades of sensitive underground experiments and collider searches, its gravitational influence is written into the structure of the universe at every scale. We now believe that dark matter makes up roughly 27% of the total energy content of the universe. Ordinary matter, atoms, stars, planets, gas, everything we can see and touch, makes up only about 5%. The rest is something even more mysterious that we will encounter later in our story. But what dark matter does for galaxies is foundational. It provides the scaffolding on which galaxies form. In the early universe, as those tiny density fluctuations began to grow under gravity, the dark matter, which interacts with gravity but not with light or other forces, was the first to collapse. It clumped together into enormous structures called dark matter halos. These halos were the first large-scale structures to form, billions of years before the first bright galaxies emerged. And it was into these dark matter halos that ordinary matter, the gas clouds of hydrogen and helium, fell. The halos acted like gravitational wells, drawing in gas from the surrounding universe. As the gas fell inward, it compressed, heated, and eventually reached densities where stars could ignite. This is the picture our best cosmological simulations give us. The Millennium Simulation, run in 2005 by Volker Sprengel and his colleagues at the Max Planck Institute for Astrophysics, modeled the gravitational evolution of 10 billion dark matter particles across a cosmic volume hundreds of millions of light-years across. What emerged, from purely physical rules, was a cosmic web strikingly similar to what we observe. Filaments. Sheets. Nodes where filaments intersect, the densest regions, where the most massive galaxy clusters would eventually form. The simulation showed, with haunting clarity, that the large-scale structure of the universe, the pattern of galaxies and voids, is not random. It is the inevitable consequence of those tiny ripples in the early universe, amplified over billions of years by the relentless action of gravity, and guided by the invisible dark matter scaffolding that pervades all of space. Dark matter is, in a very real sense, the hidden architect of everything we see. Every galaxy that has ever existed formed within a dark matter halo. Every cluster of galaxies sits within a much larger dark matter overdensity. The visible universe, all those glittering stars and luminous nebulae, is just the decoration on a vast, invisible structure that we can only infer from its gravitational effects. There is something humbling about that. Something that asks us to hold our certainties lightly. The universe is mostly things we cannot see. The universe is, in its deepest structure, invisible to us. We are glimpsing only the surface of something far deeper and stranger. And yet, from that invisible scaffolding, extraordinary things grew. The first galaxies began to emerge. And their story, unfolding over billions of years, is what we will follow through the rest of this night. Part 3, The First Galaxies, Islands of Fire in the Dark. We are now moving forward in time. The Dark Ages are ending. The first stars have ignited. And in pockets scattered across the universe, drawn together by gravity, cradled within dark matter halos, the first recognizable galaxies are beginning to take shape. This happened early. Earlier than astronomers once expected. For much of the 20th century, the prevailing intuition was that galaxies formed gradually, that they assembled slowly over billions of years as gas clouds merged and stars accumulated. The universe, after all, seemed to be a place that rewarded patience. Slow processes, unfolding over geological and cosmic timescales, producing structure from chaos. But observations of the distant, and therefore ancient, universe told a more complicated story. As telescopes became more powerful, as the Hubble Space Telescope was launched in 1990 and began returning its extraordinary deep-field images, astronomers found that even very early in the universe's history, there were already galaxies. Small ones, yes. Irregular, chaotic, nothing like the grand spirals and elegant ellipticals we see in the local universe today. But unmistakably galaxies. The Hubble Deep Field images, taken in 1995 and then again in 1998, were among the most significant photographs ever made. By pointing the Hubble Space Telescope at a tiny, apparently empty patch of sky, a region that appeared to contain almost nothing, and exposing the detector for over 10 days, astronomers revealed a field packed with thousands of galaxies. Galaxies at every stage of development. Some nearby, some so distant that their light had traveled for nearly the full age of the universe to reach us. Those images changed our understanding of galaxy formation profoundly. They showed that the early universe was not a quiet place. It was a place of furious activity. Galaxies forming rapidly, colliding, merging, bursting with star formation at rates far beyond anything we see in the modern universe. But nothing prepared astronomers for what the James Webb Space Telescope would eventually reveal. Launched on Christmas Day 2021 and reaching its operating position at the second Lagrange point a month later, the James Webb Space Telescope was designed to see further back in time than any previous instrument. With its 6.5-meter gold-coated mirror, nearly 3 times the diameter of Hubble's, and its exquisite sensitivity to infrared light, Webb could detect the light from the very earliest galaxies, whose visible light has been stretched by the universe's expansion into the infrared portion of the spectrum. When Webb's first images were released in July 2022, astronomers were astonished. Not merely by the beauty of the images, though they were extraordinary, but by what those images implied. Webb found galaxies that appeared to be far more massive, far more developed, far more organized than anything the current models of galaxy formation had predicted at those early times. Some of these galaxies appeared to be already quite large and already containing old stellar populations, meaning they had formed stars intensely and then stopped, when the universe was less than 1 billion years old. According to standard models of how galaxies grow by slowly accumulating gas and merging with smaller systems, this seemed almost impossible. There wasn't supposed to have been enough time. The astrophysicist Alison Kirkpatrick, commenting on these early Webb results, said something that captured the field's feeling perfectly. She said, "We've found something we can't explain." And in science, that is one of the most exciting sentences you can say. The leading explanation for how the first galaxies formed is called hierarchical structure formation. The idea is that small things formed first, small dark matter halos, capturing small amounts of gas, forming small clusters of stars, and then these small protogalaxies merged together to build larger and larger structures. Bottom-up assembly, as cosmologists sometimes call it. In this picture, the very first galaxies were tiny by modern standards. Perhaps a few 100 million solar masses. Compare that to the Milky Way's roughly 1 trillion solar masses. They were compact, irregular, burning furiously with star formation, and embedded in much larger dark matter halos. These early systems were also embedded in something remarkable, the reionization epoch. Recall that after recombination, when the universe became transparent, the hydrogen gas that filled space became neutral. It stayed that way through the Dark Ages. But when the first stars and early galaxies ignited, they began to pour out enormous quantities of ultraviolet radiation. This radiation was energetic enough to strip electrons from neutral hydrogen atoms, to ionize them. Over hundreds of millions of years, from roughly 200 million to perhaps 1 billion years after the Big Bang, the ultraviolet light from early galaxies and quasars gradually ionized all the neutral hydrogen in the vast spaces between galaxies. The universe underwent a phase transition, a reionization, transforming the intergalactic medium from neutral to ionized. This was a profound event in cosmic history. And one of the primary science goals of the James Webb Space Telescope is to study this epoch in detail, to find the galaxies responsible for reionizing the universe, and to understand how they did it. What we can say with confidence is that the first galaxies were extraordinary objects. Blazing with ultraviolet light. Forming stars at a furious pace. Contributing to the transformation of the universe around them. And carrying within them, even at that early age, the seeds of everything that would come later, the black holes, the chemical enrichment, the structural patterns that would eventually produce galaxies like our own. The universe was awake now, after its long dark sleep. And it was burning. Part 4. When Galaxies Collide, Mergers and the Building of Giants. One of the most dramatic processes in the life of a galaxy is not something that happens quietly from within. It is something that arrives from outside, another galaxy, drawn by gravity, approaching on a trajectory that will end in collision and transformation. Galaxy mergers are among the most spectacular events in the universe. And they are not rare. They are, in fact, one of the primary mechanisms by which galaxies grow. In the early universe, when galaxies were smaller and more closely packed, mergers were extremely common. Cosmological simulations show that the average large galaxy of today has undergone dozens, sometimes hundreds, of mergers over its lifetime. Some of these were minor events, small satellite galaxies falling into a much larger host, barely disrupting it. Others were major mergers, two galaxies of comparable size colliding and combining to create something new and different from either progenitor. The physics of galaxy mergers is deeply counterintuitive, because when we say two galaxies collide, we do not mean that stars crash into each other. Stars are so small relative to the vast distances between them that even in a galactic collision, the chance of any two individual stars making contact is vanishingly small. If you were inside a galaxy as it collided with another, you might not notice anything immediately. The stars would mostly pass by each other like ships in a vast, dark ocean. What does collide, what does interact directly, is the gas. The interstellar medium, the clouds of gas and dust that fill the space between stars, does experience the collision. Clouds run into each other, compress, heat up, and under the right conditions, trigger enormous waves of star formation. And the gravitational tidal forces that the two galaxies exert on each other reshape their structures dramatically. Astronomers Aller and Yuri Tummer published a landmark paper in 1972 that helped transform our understanding of this process. Using early computer simulations, primitive by today's standards but revolutionary at the time, they modeled the gravitational interaction between pairs of galaxies and showed that the long, beautiful tidal streams and bridges of stars seen in photographs of colliding galaxies could be explained as the gravitational response of a stellar disk to the passage of another massive system. Their simulations reproduced, with striking fidelity, the shapes of famous interacting galaxy pairs like the antennae galaxies, a pair of colliding spiral galaxies about 65 million light-years away, whose long curving tails of stars stretch out into space like the antennae of some vast cosmic insect. Or the mice galaxies, whose tidal tails stretch for nearly 600,000 light-years. These images, available in abundance from the Hubble Space Telescope's archive, are among the most beautiful in astronomy. Spirals caught in the act of embracing each other. Stars drawn out into long, luminous streamers. The geometry of gravity made visible across millions of light-years. But what does a major merger produce? What does the universe look like when two large spiral galaxies come together? The answer, generally, is an elliptical galaxy. Elliptical galaxies are among the most massive objects in the universe. Unlike spiral galaxies, with their flat disks and graceful arms, ellipticals are smooth, featureless blobs of stars, sometimes roughly spherical, sometimes elongated, containing hundreds of billions to trillions of stars. They contain very little gas and dust, very little ongoing star formation. They are, in a sense, finished galaxies. Galaxies that have used up or expelled most of their star-forming material and now shine with the red and yellow light of old, aging stars. The largest of these ellipticals, the so-called CD galaxies found at the centers of rich galaxy clusters, are the most massive stellar systems known to exist. They have grown to their enormous size through repeated mergers, swallowing galaxy after galaxy over billions of years, building up stellar populations that can exceed 10 trillion solar masses. The merger process also plays a critical role in activating the supermassive black holes that lurk at the centers of most large galaxies. When two galaxies merge, their central black holes spiral toward each other through a process of gravitational friction, and the infall of gas toward the center of the merger can fuel intense accretion onto these black holes, turning them temporarily into quasars, the brilliant beacons of the early universe. We will return to this story when we talk about black holes and their role in galaxy evolution. One of the most remarkable aspects of our own galaxy's history is how visible it makes the merger process. The Milky Way is surrounded by the debris of previous mergers. The Sagittarius dwarf galaxy has been orbiting and merging with the Milky Way for billions of years, its stars now stretched into a vast stream that wraps around the entire galaxy. The Magellanic Clouds, the two satellite galaxies visible from the southern hemisphere as faint smudges in the night sky, are currently in the process of being drawn in by the Milky Way's gravity. And in the future, roughly 4.5 billion years from now, our own galaxy will undergo the most dramatic event in its history. The Andromeda Galaxy, our nearest large neighbor, is approaching us at roughly 110 kilometers per second. In about 4 to 5 billion years, the Milky Way and Andromeda will collide and merge, creating a new, larger elliptical galaxy that some astronomers have already given the nickname Milkomeda. The collision will be a slow-motion ballet lasting hundreds of millions of years. The two galaxies will pass through each other, swing apart, fall back together, and eventually merge into a single system. The night sky, if anyone were around to see it, would be extraordinary, filled with the stars and gas of two galaxies in the process of becoming one. Our Sun, and any planets orbiting it, would most likely survive this merger intact. The Sun might be flung to a different orbit in the new combined galaxy. But life on Earth, if any were to persist for another 5 billion years, would look up at a profoundly different sky. Galaxy mergers remind us that the universe is not static. It is not a collection of fixed objects arranged in space like ornaments on a shelf. It is a dynamic, evolving system in which everything is moving, everything is interacting, everything is being transformed by its encounters with everything else. The galaxies we see today are not the galaxies that existed billions of years ago. They are the products of a long history of growth, collision, merger, and reinvention. Each one carries within its structure the record of all those encounters, written in the orbits of its stars, the distribution of its gas, the mass of its central black hole. Part 5: Stars as the Currency of Galaxies, Star Formation and the Interstellar Medium. A galaxy, at its heart, is a machine for making stars. Everything else, the dark matter halo, the central black hole, the grand spiral arms, exists in a kind of supporting relationship with the fundamental process of converting gas into stars. And to understand how galaxies form and evolve, we need to understand the life cycle of stellar matter, how gas becomes stars, and what happens when those stars die. The raw material for star formation is the interstellar medium, the gas and dust that fills the spaces between stars in a galaxy. It is not empty space. Far from it. The interstellar medium is a complex, multi-phase environment with regions of different temperatures and densities coexisting in rough balance. There are hot regions, extremely low-density gas at temperatures of millions of degrees, created by supernova explosions. There are warm regions, the diffuse ionized and neutral gas that makes up the bulk of the interstellar medium. And there are cold, dense regions, molecular clouds, the giant nurseries of stars. Molecular clouds are remarkable objects. Some of the largest, the so-called giant molecular clouds, contain millions of solar masses of gas and span hundreds of light years. They are cold, typically just a few tens of degrees above absolute zero. They are dense enough that hydrogen exists not as individual atoms but as molecules, H2, molecular hydrogen. And they are dark, obscuring the stars behind them with their dust. Within these clouds, there are regions of even higher density, clumps and cores where gravity is winning out over thermal pressure and turbulence. In these regions, the gas is collapsing. Slowly at first, then more rapidly, as the core heats up and its self-gravity increases. Eventually, the density and temperature at the center become high enough that hydrogen fusion ignites. A star is born. The process is not instantaneous. The collapse of a protostellar core takes tens of thousands to hundreds of thousands of years. During that time, the forming star is surrounded by a disk of gas and dust, a protoplanetary disk, which may eventually form planets. And the nascent star drives powerful jets of material from its poles, blowing cavities in the surrounding cloud and announcing its birth with spectacular outflows visible in infrared and radio wavelengths. The rate at which a galaxy forms stars, its star formation rate, is one of the most important quantities in galaxy evolution. And one of the most striking discoveries of modern observational astronomy is how dramatically the star formation rate of the universe has changed over time. The cosmic star formation rate was not steady. It peaked roughly 10 billion years ago, about 3 to 4 billion years after the Big Bang, when galaxies across the universe were forming stars at a rate perhaps 10 to 30 times higher than the average rate today. This peak era is sometimes called cosmic noon, the time when the universe was most actively building stars, when galaxies were blazing with ultraviolet light and infrared emission from star-forming regions. Since cosmic noon, the overall star formation rate of the universe has declined steadily. We live in a universe that is, cosmologically speaking, gradually winding down its stellar nurseries. Galaxies today form stars at a much lower rate than their ancestors did. The universe is, in a sense, aging. But why? What caused this decline? What quenched the star formation in so many galaxies? This is one of the central questions in galaxy evolution today, and the answer is almost certainly multi-layered. Several mechanisms are thought to play important roles. One is simply the consumption of gas. Stars form from gas. When a galaxy has used up its reservoir of cold gas, converting it into stars and heating the remainder with stellar radiation and supernova explosions, star formation slows and eventually stops. The galaxy runs out of fuel. Another mechanism is stellar feedback. Massive stars produce enormous amounts of ultraviolet radiation that heats and disperses the surrounding gas, making it harder for other stars to form. And when massive stars die as supernovae, the catastrophic explosions that mark the end of the lives of stars more than about 8 times the mass of the Sun, they inject vast amounts of energy and momentum into the interstellar medium. In some cases, particularly in smaller galaxies, this supernova-driven feedback can actually blow gas out of the galaxy entirely, stripping it of its star-forming material. A third, and perhaps the most powerful mechanism in large galaxies, involves the central supermassive black hole. We will explore this in detail later, but the essential point is that when a supermassive black hole is actively feeding, accreting gas and shining as a quasar, it can drive powerful winds and jets that heat and expel gas from the entire galaxy, shutting down star formation across the whole system. This process, called AGN feedback, is thought to be responsible for the death of star formation in the most massive galaxies. The interplay between star formation, stellar feedback, and black hole feedback creates a kind of self-regulating system. When gas cools and falls into a galaxy, it forms stars and feeds the black hole. The energy released by both processes then heats the gas, preventing it from cooling further. The galaxy modulates its own activity. It breathes, inhaling gas, forming stars, exhaling energy, then inhaling again. The study of the interstellar medium has been transformed in recent decades by radio and millimeter wavelength observatories. The Atacama Large Millimeter Array, ALMA, located in the Chilean desert at an altitude of 5 kilometers, is perhaps the most powerful tool we have for studying cold gas and dust in galaxies at all distances. Since it began operations in 2013, ALMA has revealed the internal structure of star-forming regions in exquisite detail, traced the cold gas reservoirs of galaxies in the early universe, and begun to show us how the raw material for stars is distributed and transported within galaxies. What these observations consistently show is that the story of stars is the story of galaxies. To trace the history of star formation across cosmic time is to trace the history of the universe's most fundamental creative act, the conversion of diffuse gas into the dense, hot, glowing furnaces of nuclear fusion that light the darkness of space. Part 6: The Spiral Galaxy, Architecture of Beauty and Mystery. When most people picture a galaxy, they picture a spiral. The classic form, a bright central bulge surrounded by a flat disk of stars, gas, and dust, from which emerge two or more sweeping arms of enhanced brightness, curving outward like the arms of a pinwheel. Spiral galaxies are among the most beautiful objects in the universe. And our own galaxy, the Milky Way, is one of them. We live inside a barred spiral galaxy, somewhere in one of its outer arms, about 26,000 light-years from the center. The discovery that our galaxy was a spiral came slowly and with difficulty, because we are inside it. Mapping the Milky Way is like trying to make a map of a city while standing in the middle of one of its neighborhoods, unable to travel, and surrounded by fog. But through careful observations of the distribution of gas clouds, star clusters, and radio emissions, astronomers pieced together a picture of our galaxy's large-scale structure over the course of the 20th century. The key tool was the 21-centimeter hydrogen emission line, radio waves emitted by neutral hydrogen atoms that were identified theoretically by Hendrik van de Hulst in 1944 and first detected in 1951. Radio waves can penetrate the dust that blocks visible light, allowing astronomers to map the distribution of gas throughout the galaxy regardless of intervening obscuration. These maps revealed the spiral structure of the Milky Way, showing the gas concentrated in distinct spiral arms. But what creates the spiral arms in the first place? This question bothered astronomers for a long time. If the arms were simply material features, fixed groups of stars and gas rotating together, they would wind up over time, becoming tighter and tighter until the spiral pattern disappeared entirely. Given the many rotations our galaxy has made since its formation, any material spiral arms should have wound up long ago. The solution to this winding problem was proposed by the Chinese-American astrophysicist C.C. Lin and his colleague Frank Hsu in 1964. They proposed that spiral arms are not material features at all. They are density waves, regions of slightly higher density that rotate through the disk of the galaxy at a different speed than the stars themselves. Think of a traffic jam on a highway. The jam, the region of high density, moves down the road independently of the individual cars that pass through it. Cars enter the jam, slow down, spend some time in it, and then emerge on the other side and speed away. The jam itself persists, even as the cars that make it up are constantly changing. Spiral arms work similarly. Stars and gas enter a spiral arm as they orbit the galaxy, spend time moving through the enhanced density region, and then emerge on the other side. As gas enters the arm and is compressed, it triggers star formation, creating the bright young blue stars and glowing nebulae that make spiral arms so visually striking in photographs. The density wave theory remains our best explanation for the long-lived spiral patterns seen in many galaxies, though the full story is more complex. Tidal interactions with companion galaxies, internal instabilities in the stellar disk, and feedback from star formation all contribute to shaping the spiral structure of individual galaxies. Our own galaxy is a barred spiral. This means that instead of a smooth central bulge from which the spiral arms emerge, the Milky Way has an elongated bar of stars running through its center, roughly 27,000 light-years long, from which the spiral arms extend at the bar's ends. Barred spirals are actually quite common, perhaps 2/3 of all spiral galaxies have some form of bar. The bar forms through a gravitational instability in the stellar disk. Stars in the disk begin to organize into elongated orbits, elongated ellipses that share a common orientation, and the collective result is a visible bar structure. Spiral galaxies also contain some of the most massive and luminous nebulae in the universe, the giant HII regions where ionized hydrogen glows red with the emission of hydrogen alpha photons, excited by the ultraviolet radiation from young, massive stars. The Orion Nebula, visible to the naked eye as a fuzzy star in the sword of Orion, is one such region in our own galaxy, a stellar nursery just 1,300 light-years away, where hundreds of young stars are forming right now. When we look at photographs of spiral galaxies, we are often seeing the light of these regions. The glowing pink and red splotches scattered along the spiral arms mark the sites of active star formation. We are looking at the galaxy's creative engine, its ongoing project of building new stars from ancient gas. There is something deeply moving about that. Looking at a photograph of a spiral galaxy and knowing that in each of those pink glowing regions, new suns are being born. New solar systems assembling from their parent nebulae. New worlds forming. The galaxy, in those regions, is making its future. And our galaxy is doing the same. Right now, as you rest here in the quiet of this night, somewhere in the Orion arm of the Milky Way, gas clouds are collapsing. Protostars are heating up. The universe is quietly, patiently, building its next generation of suns. Part 7, The Black Hole at the Center, Cosmic Engines of Transformation. At the heart of nearly every large galaxy in the universe, there sits a monster. Not a monster in any fearful sense, more a profound, almost philosophical extreme. A supermassive black hole, an object so dense, so massive, that even light cannot escape its gravitational pull. A point, or rather, a region, from which nothing returns. The evidence for supermassive black holes at the centers of galaxies came together slowly over the second half of the 20th century. Astronomers had noticed since the early 20th century that the centers of some galaxies were extraordinarily bright, far brighter than a normal accumulation of stars could explain. These active galactic nuclei, as they came to be called, were sometimes so luminous that they outshone the rest of their host galaxy by factors of hundreds. The most extreme cases were quasars, quasi-stellar radio sources, Discovered in the early 1960s when astronomers matched bright radio sources with optical counterparts that looked like stars but showed spectral lines shifted enormously to the red. Their redshifts indicated that they were at cosmological distances, billions of light-years away. And if they were that far away and still appeared that bright, they must be producing energy at a staggering rate. More energy than thousands of galaxies combined, from a region not much larger than our solar system. Astronomer Martin Schmidt, at Caltech, made the critical identification in 1963. He determined the redshift of the quasar 3C273 and realized what it implied: this was no ordinary object. It was something radiating energy at a rate of perhaps 4 trillion times the luminosity of the Sun, from a source smaller than a light-year across. The theoretical explanation that eventually won out was accretion onto a supermassive black hole. As matter falls toward a black hole, orbiting faster and faster as it spirals inward, forming an accretion disk, it heats up to temperatures of millions of degrees and radiates enormous amounts of energy across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. This process is extraordinarily efficient, far more efficient than nuclear fusion in stellar cores. A few % of the mass energy of accreted matter can be converted into radiation, making an actively feeding supermassive black hole the most efficient power source in the universe. The black holes involved are not merely large. They are staggeringly large. The supermassive black hole at the center of our own Milky Way, known as Sagittarius A*, pronounced Sagittarius A*, has a mass of roughly 4 million times the mass of the Sun. And it is one of the smaller supermassive black holes known. The black hole at the center of the giant elliptical galaxy M87, imaged for the first time by the Event Horizon Telescope collaboration in 2019, has a mass of 6.5 billion solar masses. 6.5 billion suns compressed into a region smaller than our solar system. The image of that black hole, a glowing ring of orange-hot gas surrounding a dark central shadow, was one of the most extraordinary scientific achievements of the 21st century. A moment when humanity truly saw, for the first time, the edge of a black hole. And then, in 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A* itself. Our own galaxy's black hole, seen at last, a fuzzy ring of light, the shadow cast by the event horizon against the glowing accretion of surrounding gas. But what do these black holes have to do with the galaxies that surround them? Are they merely curiosities lurking at the center, or do they play an active role in shaping their host galaxies? The answer, we now believe, is that they play an absolutely central role. The supermassive black hole and its host galaxy are deeply intertwined, connected by a relationship that astronomers sometimes call coevolution. The first hint of this connection came from a surprising discovery in the 1990s. Astronomers found that the mass of the central black hole in a galaxy was tightly correlated with properties of the galaxy's bulge, particularly with the velocity dispersion of stars in the bulge, a measure of how fast those stars are moving and therefore how massive the bulge is. This is called the M-sigma relation, first clearly identified by Laura Ferraris and David Merritt, and independently by Carl Gebhardt and colleagues, in 2000. The correlation was startling in its precision. Galaxies with more massive bulges had more massive black holes, and the relationship followed a remarkably tight power law across orders of magnitude in black hole mass. Whatever was determining the growth of the galaxy's stellar bulge seemed also to be determining the growth of the black hole, even though the black hole's sphere of direct gravitational influence was millions of times smaller than the bulge. This implied a feedback mechanism. Something about the activity of the black hole, the energy and momentum it releases when it is actively accreting, when it shines as a quasar, must be influencing the growth of the surrounding galaxy. When the black hole grows too large and its energy output becomes too intense, it can drive powerful winds that sweep gas out of the galaxy, shutting down star formation. This is AGN feedback, feedback from the active galactic nucleus. Computer simulations of galaxy evolution that include AGN feedback produce results that match observations remarkably well. Without AGN feedback, simulations produce too many massive, star-forming galaxies. They can't explain why the most massive galaxies today are old, red, and largely dead. With AGN feedback included, the simulations reproduce the observed population of galaxies far more accurately. This has led to a picture in which the supermassive black hole acts as a kind of thermostat for its host galaxy. It regulates how much gas cools and forms stars. When star formation gets too active, more gas falls to the center, feeding the black hole, which then drives winds and jets that heat the gas and shut down the cooling. When star formation drops off, less gas reaches the center, the black hole quiets down, and eventually gas can cool again. Galaxies breathe. They cycle through periods of activity and quiet, regulated in part by the restless engine at their core. In the early universe, when gas was abundant and galaxies were dense with cold material, black holes grew rapidly and quasars blazed. As the universe aged and its gas supply dwindled, the most massive black holes were quieted, their host galaxies' star formation suppressed. The bright, violent youth of the universe gave way to the more sedate, aging universe we inhabit today. There is something almost mythological about it, the monster at the center of the galaxy, shaping the destinies of the stars around it, governing growth and quenching creation with the force of its breath. Part 8, The Chemical Enrichment of the Universe, How Galaxies Build Complexity. Every atom of carbon in every living cell. Every atom of oxygen you breathe. Every atom of iron in your blood. They were not present in the universe at the beginning. They were made inside stars. This is one of the most profound truths in all of science, and it connects the story of galaxies directly to the story of life itself. The evolution of galaxies is not just an astrophysical abstraction, it is the story of how the raw materials for chemistry, for biology, for complexity of every kind, were built up over billions of years inside the furnaces of dying stars and scattered into the cosmos. Inside the core of an ordinary star like the Sun, hydrogen is fused into helium. For the Sun, this process will continue for another 5 billion years. When the hydrogen in the core is exhausted, the core will contract and heat up, and helium will begin to fuse into carbon and oxygen. The Sun will swell into a red giant, briefly making heavier elements before expelling its outer layers as a beautiful planetary nebula, leaving behind a dense remnant called a white dwarf. More massive stars go further. In stars with masses several times that of the Sun, nuclear fusion can proceed through carbon, oxygen, neon, silicon, and ultimately to iron. Iron is the endpoint of stellar nuclear fusion. It cannot release energy by fusing with itself or lighter elements, and it cannot release energy by fissioning. When an iron core forms at the center of a massive star, the core becomes unstable. In a fraction of a second, it collapses to a neutron star or black hole, and the outer layers of the star explode in a supernova, one of the most energetic events in the universe. A supernova releases, in a matter of seconds, more energy than the Sun will emit over its entire 10 billion-year lifetime. It briefly outshines its entire host galaxy. And in the process, it does two things crucial for the chemical evolution of the universe. First, it creates elements heavier than iron, through a process called the R process, rapid neutron capture, where nuclei are bombarded with neutrons so rapidly that they build up to very heavy elements before they have time to undergo radioactive decay. Second, it disperses all the elements synthesized during the star's lifetime, including those heavy elements, into the surrounding interstellar medium. The explosion spreads the chemical legacy of that star across thousands of light years. The gas it ejects will eventually cool, mix with other gas clouds, and eventually be incorporated into new generations of stars and planets. The gold in your jewelry, the uranium in nuclear reactors, the iodine in your body, all of it was created in the violent deaths of massive stars. In 2017, a gravitational wave event called GW 170817 provided additional confirmation for the R process. Two neutron stars, the dense remnants of massive star deaths, were detected merging together, generating gravitational waves and a spectacular electromagnetic signal called a kilonova. Spectral analysis of the kilonova revealed the presence of heavy R process elements, including strontium. The merger of two neutron stars had synthesized gold, platinum, and other heavy elements in the debris cloud, before scattering them into space. Over the history of a galaxy, this process of chemical enrichment proceeds generation by generation. Each successive generation of stars inherits gas that has been slightly enriched by the previous generation. The first stars, made from pure hydrogen and helium, produced the first batch of heavier elements. The second generation inherited those elements, made more, and scattered them. And so on, through generation after generation of stellar birth and death. This means that older stars, formed early in the universe, have lower metallicity, a lower abundance of elements heavier than hydrogen and helium. Younger stars, formed from gas that has been enriched by many previous generations, have higher metallicity. Astronomers can use the metallicity of a star as a rough guide to its age and the conditions under which it formed. Our Sun, formed about 4.5 billion years ago, has a metallicity that reflects billions of years of chemical enrichment in the Milky Way. It contains about 2% by mass of elements heavier than hydrogen and helium, a small fraction, but enough to form a rocky inner solar system, complex molecular chemistry, and ultimately life. The study of chemical evolution in galaxies, how metallicity builds up over time, how it varies across different regions of a galaxy, how it correlates with galaxy mass and star formation history, is one of the richest fields in contemporary astrophysics. Large spectroscopic surveys, mapping the chemical compositions of millions of stars across the Milky Way and in nearby galaxies, are revealing the detailed chemical history of our cosmic neighborhood with unprecedented resolution. Projects like the Gala survey in Australia, the Apogee survey in the United States, and the Gaia mission of the European Space Agency are together building what astronomers call a chemical fingerprint of the Milky Way. By measuring the abundances of dozens of elements in hundreds of thousands of stars, they can reconstruct which stars formed together, which ones were brought in from dwarf galaxies that were absorbed in past mergers, and how the chemical composition of the galaxy has changed over its 14 billion year history. The universe is not just building stars and galaxies. It is building complexity. It is building the alphabet of chemistry, one element at a time, over billions of years, through the patient labor of stars. And in the fullness of time, that complexity gave rise to molecules, to organic chemistry, to the possibility of life. The connection between galaxy evolution and the existence of life in the universe is not metaphorical. It is direct and physical. We are, as the astronomer Carl Sagan said, made of star stuff. The iron in our blood was forged in a stellar core. The calcium in our bones was scattered by a stellar wind. We are the universe becoming aware of itself, built from the debris of a billion ancient suns. Part 9: Galaxy Clusters and the Largest Structures in the Cosmos. Step back now from the individual galaxy. Step back from the single island of stars with its dark matter halo and its central black hole and its generations of stellar birth and death. Step back far enough that individual galaxies become dots of light, too small to resolve. What you see, at that scale, is structure. Enormous structure, spanning tens and hundreds of millions of light years. Galaxies are not distributed uniformly through space. They gather into groups. Groups gather into clusters. Clusters gather into superclusters. And superclusters are arranged into the filaments, sheets, and voids of the cosmic web we first encountered in our discussion of dark matter. Galaxy clusters are the largest gravitationally bound structures in the universe. A rich cluster may contain hundreds or thousands of individual galaxies, all orbiting within a common gravitational potential well, embedded in a hot plasma of ionized gas called the intercluster medium, and pervaded by a vast dark matter halo that provides most of the cluster's total mass. The total mass of a large galaxy cluster can be 1,000 trillion solar masses, a quadrillion times the mass of the Sun. And yet, when you look at a photograph of a cluster, you see mostly empty space. Even within a cluster, galaxies are separated by vast distances. The cluster is, in a sense, mostly nothing, but that nothing is structured, shaped by dark matter and the hot gas that fills it. The intercluster medium, that hot plasma filling the space between galaxies in a cluster, is extraordinary in its own right. It has been heated to temperatures of tens of millions of degrees by the gravitational energy released as gas fell into the cluster. At those temperatures, it emits X-rays, and clusters are among the brightest X-ray sources in the sky. Observatories like the Chandra X-ray Observatory, launched in 1999, have mapped this hot gas in exquisite detail, revealing its complex structure, bubbles blown by the jets of central black holes, cold fronts where gas of different temperatures meets, shock waves from merging subclusters. One of the most important cosmological tools of the late 20th and early 21st centuries has been the use of galaxy clusters to measure the properties of the universe. Clusters are sensitive cosmological probes because their abundance, how many clusters of a given mass exist at a given epoch, depends sensitively on the cosmological parameters that govern the universe's expansion and structure growth. This approach has helped pin down the density of dark matter, confirmed the existence of dark energy, which we will discuss shortly, and tested models of structure formation in many important ways. But clusters are also fascinating as environments for galaxy evolution. The dense environment of a galaxy cluster subjects its member galaxies to processes that have no counterpart in more isolated regions of the universe. One of the most dramatic is ram pressure stripping. As a galaxy moves through the hot, dense intercluster medium, it experiences a wind of hot gas, much like a car moving through air, but at cosmic scales. This wind can strip the galaxy's cold gas, its star-forming fuel, away from it, quenching star formation. The stripped gas forms spectacular tails behind the galaxy, visible in both radio and X-ray observations. The jellyfish galaxies are a striking example. These are galaxies caught in the process of being stripped, their gas tails trailing behind them like the tentacles of a jellyfish, or perhaps like a comet's tail, swept back by the force of the surrounding medium. In some cases, the stripped gas continues to form stars, creating a trail of young stars and star-forming clumps extending behind the galaxy as it moves through the cluster. Another important process is galaxy harassment, the cumulative effect of many high-speed gravitational encounters with other cluster galaxies and with the cluster potential itself. Unlike major mergers, which are violent and relatively rare, harassment consists of many gentle gravitational nudges over billions of years, gradually heating and disturbing the stellar disk, potentially transforming spirals into lenticular or irregular galaxies. Galaxy clusters also concentrate gravitational lensing effects. The enormous mass of a cluster, both the visible galaxies and the far more massive dark matter and hot gas, bends light from background objects, creating dramatic arcs and distortions of distant galaxies behind the cluster. This gravitational lensing effect, first predicted by Einstein's general relativity, was confirmed observationally in 1987 when arcs were discovered around the cluster Abell 370. Today, gravitational lensing by clusters is one of our most powerful tools for mapping dark matter. By analyzing the distorted shapes of background galaxies, astronomers can reconstruct the distribution of mass, including invisible dark matter, within the foreground cluster. The result is a dark matter map, revealing the hidden architecture of the most massive structures in the universe. Perhaps the most famous demonstration of this technique came from observations of the Bullet Cluster, two galaxy clusters that have recently passed through each other. When the two clusters collided, the hot gas in each cluster slowed down due to electromagnetic interactions, but the dark matter and galaxies, which interact only gravitationally, passed through relatively unimpeded. The result is a system where the hot gas, detected in X-rays, is offset from the dark matter, mapped by gravitational lensing. The dark matter has separated from the ordinary matter. This observation, published by Douglas Clow and colleagues in 2006, is considered one of the most direct pieces of evidence for dark matter's existence. It is very difficult to explain the Bullet Cluster without invoking some form of non-baryonic dark matter, matter that behaves gravitationally but doesn't interact electromagnetically. Beyond clusters lie the superclusters, vast, loosely bound aggregations of many galaxy clusters, spanning hundreds of millions of light-years. Our own galaxy sits within the local group, a modest collection of about 50 galaxies dominated by the Milky Way and Andromeda. The local group is part of the Virgo supercluster, which in turn is part of an even larger structure, the Laniakea supercluster, identified in 2014 by Brent Tully and his colleagues at the University of Hawaii. Laniakea, the name means immeasurable heaven in Hawaiian, spans roughly 500 million light-years and contains the mass of 100 quadrillion suns. It is bounded by regions where the gravitational flow of galaxies diverges, where galaxies, instead of falling toward Laniakea's center, flow away. We live within this immeasurable heaven, somewhere near its edge, an unremarkable spiral galaxy in an unremarkable cluster in one of the largest structures the universe has managed to build. Part 10: Dark Energy and the Fate of Galaxies, the Accelerating Universe. We have been moving through the history of galaxies from the beginning of time toward the present. But the story does not end with the present. The universe has a future. Galaxies have a future. And that future is shaped by the most mysterious ingredient in the cosmic recipe. In 1998, two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, announced a discovery that shocked the scientific world. The expansion of the universe was not slowing down, as gravity would dictate. It was speeding up. To make this measurement, both teams had been studying Type Ia supernovae, a special category of stellar explosion in which a white dwarf accretes material from a companion star until it exceeds a critical mass and explodes. Because the critical mass is always the same, these supernovae always explode with approximately the same intrinsic brightness. They are what astronomers call standard candles, objects whose true luminosity is known, allowing distance to be inferred from apparent brightness. By measuring the distances and recession velocities of Type Ia supernovae at various cosmological distances, both teams found that the supernovae were farther away than expected, farther than they should be if the universe's expansion were decelerating under the influence of gravity alone. The only explanation was that something was driving the expansion to accelerate. Something was working against gravity at the largest scales, pushing the fabric of space outward at an ever-increasing rate. This something came to be called dark energy. Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011 for this discovery. What dark energy actually is remains one of the deepest unsolved problems in physics. The simplest mathematical description of it is as a cosmological constant, a term that Albert Einstein himself introduced into his equations of general relativity in 1917, and later called his greatest mistake, and which now appears to be describing something real about the universe. In quantum field theory, dark energy might correspond to the energy of the vacuum, the irreducible, quantum mechanical energy of empty space. But when physicists calculate what this vacuum energy should be from first principles, they get a number roughly 120 orders of magnitude larger than what is observed. This discrepancy, arguably the largest discrepancy between theory and observation in the history of science, has not yet been resolved. What we can say is that dark energy appears to make up about 68% of the total energy content of the universe. It is the dominant component. Everything else, dark matter, ordinary matter, radiation, together makes up only about 32%. We live in a universe that is mostly made of something we do not understand. Dark energy's effect on the future of galaxies and galaxy clusters is profound and, in some ways, melancholy. Because dark energy is accelerating the expansion of the universe, objects that are not gravitationally bound to each other are moving apart at an ever-increasing rate. In the distant future, tens of billions of years from now, Even galaxy clusters that are today relatively close will have receded beyond the cosmological horizon of any galaxy within them. The universe will become increasingly isolated. Gravitationally bound structures, individual galaxies, galaxy clusters, the local group, will remain intact, holding together against the expansion. But the vast cosmic web, the filaments and sheets, will thin and dissipate as dark energy pushes their component galaxies beyond reach. In the very far future, hundreds of billions to trillions of years from now, the remaining stars and galaxies will age and die. Massive stars die quickly, in millions of years. But low-mass stars, the red dwarfs that make up the majority of all stars in the universe, burn so slowly that they can live for trillions of years. In the far future, when all the sun-like stars have long since become white dwarfs, cooling slowly toward absolute zero, the universe will be a realm of red dwarfs burning dimly in the darkness. Eventually, even those will burn out. Stellar remnants, white dwarfs, neutron stars, black holes, will dominate the universe. Over unimaginably long timescales, protons themselves may decay, dissolving the remaining matter. Black holes will evaporate through Hawking radiation, a process theorized by Stephen Hawking in 1974 but never yet directly observed, whereby quantum effects near the event horizon allow black holes to slowly radiate energy and eventually disappear in a final burst of radiation. This is the far future of galaxies, not a violent end, but a slow, quiet dissolution. A cooling. A darkening. An eventual thermodynamic equilibrium in which nothing new is created, nothing burns, nothing stirs. The heat death of the universe. But that end is so far away as to be beyond any normal human conception of time. The current age of the universe is 13.8 billion years. The last red dwarf stars will burn for another 10 trillion years. The evaporation of the last black holes will take roughly 10 to the 100 power years, a number with 100 zeros after it. We are, cosmologically speaking, in the early morning of the universe. The stars are still burning. Galaxies are still forming, still evolving, still building new generations of stars and planets. The universe is aging, but it is not yet old. And in this early morning, on one small planet orbiting one ordinary star in one ordinary spiral galaxy, a species of curious, pattern-seeking beings built instruments sensitive enough to see the edges of the universe and patient enough to read its history from the light of a billion ancient suns. Part 11, The Milky Way, Our Own Galaxy's Biography. All the abstract grandeur of galaxy formation, all the vast cosmological machinery we have been describing, it has a local, intimate embodiment. It is the galaxy we call home. The Milky Way. Look up on a clear night, far from city lights, and you will see it, a faint, diffuse band of light stretching across the sky, from horizon to horizon. This is the disk of our galaxy, seen edge-on from our position within it. That hazy light is the combined glow of hundreds of billions of stars too distant to be resolved individually by the naked eye. The dense central bulge of the galaxy, rising toward the center of the band, glows a little brighter, pointing toward the constellation Sagittarius, toward the galactic center and the black hole that lurks there. The Milky Way has a diameter of about 100,000 light-years. Its disk is perhaps 1,000 light-years thick in most places, though with a significant warp. The outer disk is not flat but tilted, probably due to past gravitational interactions with the Magellanic Clouds. It contains between 100 and 400 billion stars. It has a central bar roughly 27,000 light-years long. It has at least 4 major spiral arms, the Normator arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm, and a minor arm called the Orion Cygnus arm, in which our solar system resides. Our Sun is located about 26,000 light-years from the galactic center, slightly above the midplane of the disk. It orbits the galactic center at a speed of about 220 kilometers per second, completing one full orbit every 225 to 250 million years, a period sometimes called a cosmic year. The Milky Way formed roughly 13 billion years ago, not long after the Big Bang, from the collapse of a protogalactic cloud within its massive dark matter halo. The oldest stars in the galaxy, found in the central bulge and in the ancient stellar halos and globular clusters that surround the disk, date to within the first billion years of the universe. The Milky Way's early history was, like all galaxies of its generation, one of rapid star formation and chaotic merger activity. Small protogalaxies fell together, combining their stellar populations, their gas reservoirs, their dark matter halos. The thick disk of the Milky Way, a distinct stellar population somewhat older and kinematically hotter than the thin disk we see today, likely formed during this chaotic early epoch, when mergers were frequent and the galaxy had not yet settled into its current orderly rotation. The thin disk, where most of the ongoing star formation occurs and where our Sun resides, formed later, as the galaxy's merger activity quieted and gas slowly settled into a flat, rotating structure. The precise timeline of this transition is still being reconstructed from the chemical and kinematic properties of stars across the disk. The Gaia mission of the European Space Agency has been transformational in this regard. Launched in 2013, Gaia has measured the positions and motions of nearly 2 billion stars in the Milky Way with a precision that was unimaginable even a decade before its launch. From those measurements, astronomers have been able to identify streams of stars that were once part of galaxies swallowed by the Milky Way billions of years ago. Their orbits still carry the memory of their origin. In 2018, a major announcement emerged from the Gaia data. Astronomers Amina Helmi and her colleagues identified the remnant of a large ancient merger, a galaxy that collided with the Milky Way roughly 10 billion years ago, contributing perhaps half of the mass of the interstellar halo. They named this ancient interloper the Gaia-Enceladus merger event, after the Greek giant imprisoned beneath a mountain. The stars of Gaia-Enceladus are still orbiting in the Milky Way today, their distinctive kinematic and chemical signatures marking them as immigrants from a vanished galaxy. This discovery reframed the Milky Way's early history. Our galaxy, serene and orderly as it appears today, underwent a violent collision in its youth that dramatically reshaped it. The interstellar halo, the thick disk, perhaps even aspects of the central bulge, all bear the imprint of that ancient collision. The Milky Way's central black hole, Sagittarius A*, was likely far more active in the distant past. There is growing evidence that it underwent periods of significant accretion activity, producing powerful winds and jets that influenced the distribution of gas in the inner galaxy. A vast structure called the Fermi bubbles, two enormous lobes of high-energy gas extending 25,000 light-years above and below the galactic plane, may be the remnant of one such ancient outburst, when Sagittarius A** fed more vigorously and drove material into the galactic halo. Today, Sagittarius A* is quiescent. It accretes very little material, producing only modest flares of X-ray and infrared emission. Our galaxy has settled into a relatively quiet middle age. There is an important sense in which the Milky Way's history is the template for understanding all galaxies. Because it is our home, close enough to study in extraordinary detail, we can reconstruct its past with a precision impossible for any external galaxy. We can read its history in the ages and compositions of its stars, in the orbits of its stellar streams, in the chemistry of its gas clouds and ancient star clusters. The Milky Way is, in a sense, our Rosetta Stone for galaxy evolution. By deciphering its history, we build and test the models we then apply to the thousands of other galaxies we observe across the cosmos. The local and the cosmic illuminate each other, page by page. And there is something quietly profound about standing beneath a clear night sky and knowing that the faint band of light above you is not just a beautiful sight, but a biography. Billions of years of history. Mergers and star formation and chemical enrichment and the slow settling of chaos into order. A galaxy that made our sun, and through our sun made us. A galaxy that was ancient when our planet formed, and will continue for billions of years after we are gone. Part 12, What We Still Do Not Know, The Open Questions at the Frontier. Throughout this long journey from the Big Bang to the present day, from the first seeds of structure in the cosmic microwave background to the vast web of galaxy clusters and superclusters that fills the observable universe, we have followed the story of how galaxies form and evolve. It is a story that science has assembled, piece by piece, observation by observation, theory by theory, over more than a century of inquiry. And yet, as with every great scientific story, the most honest and perhaps most beautiful thing we can say at its end is this: we do not fully understand it yet. There are open questions at every frontier. Puzzles that current theories cannot explain. Observations that demand new physics, new ideas, new ways of thinking about the universe. Let us sit with some of these open questions now, not as sources of frustration, but as invitations. As the places where the universe is still whispering secrets it has not yet fully told us. The first great open question is the nature of dark matter itself. We have established its existence beyond reasonable doubt. Its gravitational influence is visible at every scale, from the rotation curves of individual galaxies to the large-scale structure of the cosmic web to the temperature fluctuations in the cosmic microwave background. But we do not know what it is. For decades, the leading candidate was a class of particles called weakly interacting massive particles, or WIMPs. These hypothetical particles would have been produced in the early universe, would interact with ordinary matter only through gravity and the weak nuclear force, and would have a mass in the range of tens to hundreds of times the proton mass, conveniently within the reach of particle physics experiments. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, was expected to find evidence of WIMP dark matter. Sensitive underground detectors, shielded from cosmic rays by miles of rock, were built to detect the occasional collision of a WIMP with an ordinary atomic nucleus. Space-based observatories searched for the gamma rays that would be produced if WIMPs annihilated with each other in dense regions of the universe. None of these searches has found dark matter. The experiments have become more sensitive, the searches more thorough, the parameter space more constrained, and nothing. Either dark matter is not WIMPs, or its properties place it in regions of parameter space that our current experiments cannot reach. Alternative candidates abound. Axions, extremely light, weakly interacting particles, are now among the most actively pursued dark matter candidates, with a new generation of experiments designed to detect them. Primordial black holes formed in the early universe before star formation began, have been revisited as dark matter candidates, though observations, particularly of gravitational microlensing events, constrain how much of the dark matter they can account for. Some physicists have proposed modifications to gravity itself, modified Newtonian dynamics, proposed by Mordechai Milgram in 1983, as an alternative to dark matter. MOND works surprisingly well for explaining the rotation curves of individual galaxies but struggles to explain the large-scale structure of the universe and the behavior of galaxy clusters. Most cosmologists regard it as incomplete at best. The nature of dark energy is perhaps an even deeper mystery. The cosmological constant remains the simplest and most observationally successful description of dark energy, but it offers no physical understanding. What is the vacuum energy? Why does it have exactly the value it has? Is dark energy truly constant, or does it evolve with time? Future surveys, including the Euclid satellite of the European Space Agency, launched in 2023, and the Rubin Observatory Legacy Survey of Space and Time beginning operations in the 2020s, aim to measure dark energy's properties with far greater precision, potentially revealing whether it deviates from the simplest cosmological constant behavior. The second great open question is the tension in measurements of the Hubble constant, the rate at which the universe is currently expanding. There are two primary ways to measure the Hubble constant. One uses the cosmic microwave background and the physics of the early universe, a method that has been carried out with extraordinary precision by the Planck satellite. The other uses the cosmic distance ladder, a chain of distance measurements from nearby Cepheid variable stars to distant Type Ia supernovae, a method refined over decades by teams including Adam Rees and Wendy Friedman. The problem is that these two methods give different answers. The early universe method gives a Hubble constant of about 67 km per second per megaparsec. The distance ladder method gives about 73. The discrepancy is now at a statistical significance of roughly 5 sigma, what scientists generally regard as a detection. The chance that it is a statistical fluctuation is 1 in a million or less. This tension, called the Hubble tension, is one of the most discussed problems in modern cosmology. It could be the result of systematic errors in one or both measurement methods. Or it could be a sign of new physics, something happening in the early universe, or in the late universe, that our standard cosmological model does not account for. Early dark energy, a component of dark energy that was significant in the early universe and then decayed away, is one proposed solution. Interacting dark matter-dark energy scenarios are another. The James Webb Space Telescope is contributing to this puzzle by providing independent checks on the distance ladder. A third open question concerns the formation of the first galaxies and the mysterious tension between the massive, evolved galaxies found by Webb at very early cosmic times and the predictions of standard galaxy formation models. As we mentioned earlier, Webb found galaxies at redshifts greater than 10, when the universe was less than 500 million years old, that appear to be more massive and more structurally evolved than the standard models predict. Some of these galaxies seem to have stellar masses of tens of billions of solar masses, assembled in a tiny fraction of the universe's current age. Several explanations have been proposed. Perhaps the initial mass function of stars in the early universe was different, skewed toward more massive stars, which produce more light per unit mass, making these galaxies appear more massive than they actually are. Perhaps early black holes contributed more to the ultraviolet luminosity of early galaxies, inflating apparent stellar masses. Perhaps galaxy formation in the early universe was simply more efficient than our models suggest. Perhaps the cold, dense gas of the early universe could collapse and form stars faster than we imagined. Or perhaps our cosmological model itself needs modification. Perhaps the universe is slightly older than we think, giving early galaxies more time to grow. Perhaps dark matter behaves differently in the early universe. The James Webb Space Telescope is still relatively young in its scientific mission, and the community is still processing and debating its findings. The coming years will be crucial. A fourth open question concerns the fate of star formation, the quenching problem. We know that star formation has declined dramatically since cosmic noon. We believe that feedback from stellar winds, supernovae, and active galactic nuclei is responsible. But the details of how these processes work, how efficiently they remove gas from galaxies, how they depend on galaxy mass and environment, these remain subjects of intense study and debate. The difficulty is that the relevant physical processes span an enormous range of scales, from the parsec scale dynamics around individual supernovae to the megaparsec scale effects of AGN jets on the intercluster medium. Simulating this range of scales simultaneously is computationally intractable with current technology. Different groups use different approximations and subgrid recipes to handle the physics they cannot directly simulate, and the results depend sensitively on those choices. Simulations like Illustrious TNG, Eagle, Fire, and Simba have each made remarkable progress in reproducing observed galaxy properties from first principles. They produce virtual universes that look strikingly similar to the real one in many respects. But they disagree with each other, and sometimes with observations, in important details, revealing how much uncertainty remains in our understanding of the feedback processes that shape galaxy evolution. A fifth open question is the origin and growth of supermassive black holes. We know they exist. We know they correlate with their host galaxies in the ways described by the M-sigma relation. We know they were already enormous in the early universe, quasars at redshifts greater than 7, when the universe was less than 800 million years old, host black holes with masses of several billion solar masses. How did they grow so large, so fast? The standard picture of black hole growth, accretion of gas at a rate limited by the Eddington limit, the point at which radiation pressure balances gravity and prevents further infall, struggles to explain black holes so massive at such early times. Even if a seed black hole of 1,000 solar masses formed at redshift 20 and accreted continuously at the Eddington limit, it would barely reach a billion solar masses by redshift 7. Proposed solutions include super-Eddington accretion rates that exceed the classical Eddington limit, perhaps because the accreted gas is geometrically thick and traps the radiation before it can escape. Or the formation of massive black hole seeds, direct collapse black holes, formed from the direct collapse of massive gas clouds in the early universe without passing through a stellar phase, producing seeds of perhaps 100,000 to 1 million solar masses that can grow to supermassive scales more quickly. The James Webb Space Telescope has already found evidence for accreting massive black holes at extraordinary early epochs, including objects called little red dots, compact, red objects whose spectra suggest actively accreting black holes of substantial mass when the universe was only a few 100 million years old. Understanding these objects will be one of the central challenges of observational cosmology in the coming decade. A sixth open question, perhaps the most philosophically profound, is the question of cosmic origins. The standard Big Bang model describes the evolution of the universe from an initial hot, dense state. But what preceded that state? What caused the Big Bang? Is the Big Bang itself the beginning of time, or is it a transition, perhaps a bounce from a previous contracting phase, or the nucleation of a bubble in an eternal inflationary multiverse? Inflationary cosmology, the idea, developed by Alan Guth, André Linde, and others in the early 1980s, that the universe underwent a period of exponentially rapid expansion in its first fraction of a second, successfully explains many features of the observable universe, including the flatness of its geometry, the uniformity of the cosmic microwave background, and the origin of the density fluctuations that seeded structure formation. But inflation is a framework, not a unique theory. There are hundreds of inflationary models, each predicting slightly different things, and distinguishing between them observationally has proven very difficult. These open questions are not signs of failure. They are signs of a science that is alive, that is pushing at its own boundaries, that is honest about the limits of its current understanding. Every great discovery in the history of astronomy opened new questions even as it closed old ones. The discovery of dark matter opened the question of what it is. The discovery of dark energy opened the question of why the vacuum has energy. The discovery of cosmic acceleration opened the question of whether the universe is one of many. The history of galaxy formation and evolution is not a story with a fixed ending. It is a story still being written. By observatories on mountaintops and in orbit. By supercomputers running trillion particle simulations. By theorists drawing connections between the physics of the very small and the structure of the very large. By graduate students at their desks late at night, poring over data from the James Webb Space Telescope, looking for the one strange object that doesn't fit the existing model. It is a story written in light, in the ancient photons that have traveled billions of years to reach our instruments. And in the minds of the people patient and curious enough to read what those photons say. Closing meditation. We have traveled a long way tonight. From the first moments after the Big Bang, through the long dark silence before the first stars, to the blazing dawn of the first galaxies, the long drama of mergers and star formation and chemical enrichment, the hidden scaffolding of dark matter and the mysterious push of dark energy, and finally to the open questions that await the astronomers of the future. And here you are, resting quietly on a small, rocky planet, orbiting a middle-aged yellow star, in one of the outer spiral arms of a barred spiral galaxy, in a small group of galaxies at the edge of a supercluster that stretches 500 million light-years across. You are made of the universe's oldest work. Carbon forged in stellar cores that exploded before our sun was born. Oxygen scattered by ancient winds. Iron built in the final seconds of a dying star's life. You are, in the most literal sense, the universe's attempt to understand itself. Let that thought settle gently now. You don't need to hold the scale of it. You don't need to comprehend a trillion stars, or a billion galaxies, or 13 billion years. Simply rest in the knowledge that you are part of this vast, ancient, endlessly unfolding story. That the same forces that shape the first galaxies shape the star that warms your days and the planet beneath your feet. The universe is still here. It is still expanding, still building, still evolving. And so are you. Let your breath slow now. Let the darkness be gentle. Let the weight of the cosmos, for just this moment, be something comforting rather than overwhelming, the weight of belonging to something ancient and immense. Sleep now. Rest in the quiet of the universe's ongoing story. You are home. If you're still awake, the universe is vast and full of wonder. Subscribe to Cosmos and Dreams for a new discovery every week. Sweet dreams.